Okay, let us now go for oxidative ozonolysis. See, in this type of ozonolysis, let us consider something unsymmetric. Okay, we can go for ozone water or ozone water or hydrogen peroxide water, then hydrogen peroxide along with an oxidizing agent, like for example, silver oxide. We'll tell you the difference when silver oxide is used later, but let us first see what happens in oxidative ozonolysis. See, this part becomes carboxylic acid. Initially, supposing if you consider the basic reductive ozonolysis, we know that it becomes an aldehyde. But because this is oxidative ozonolysis, the aldehyde formed is further oxidized to acid, right? That is a speciality. And on to the other hand, of course, in reductive ozonolysis, we get ketones. As ketones are difficult to oxidize, they remain as such. Okay. So ketones are difficult to oxidize. The reason why these have got no further step. So from this end, we get a carboxylic acid, whereas from the other end, we get ketones. And supposing if we take an example of this type, say if propene is taken, right? Ozone followed by hydrolysis. As usual, you cut it here. Now this one becomes acetic acid, right? From this end, you get acetic acid, and from this end, of course, if you consider reductive ozonolysis, this area becomes formaldehyde. But because this is oxidative ozonolysis, formaldehyde so formed further gets oxidized to formic acid. And I have an interesting point here. Now, if suppose silver oxide is used, okay, if silver oxide is used, this formic acid is further oxidized. Is further oxidized to carbon dioxide. So that is the extra step that occurs with silver oxide. Less frequently used, but it's better if you remember that. If silver oxide is used, this gets further oxidized to carbon dioxide. I mean, further oxidation step. Aldehydes to acids, acids to carbon dioxide. So this is how it happens. Now there is something which is similar to this. Okay, we'll go for that. That is with the hot alkaline KMnO4. It's called oxidative cleavage. Oxidative cleavage, same as what you have seen earlier with oxidative ozonolysis. Here we'll be using the hot alkaline potassium permanganate. Okay. Now let us take the reactions with hot alkaline KMnO4. Okay. This one. See, when this is taken into consideration, okay, cut it here. You will be getting a ketone from this end and an acid, same as oxidative ozonolysis. Let me write that. And this reaction with the hot alkaline KMnO4 is very important. Okay, this is what we get. Next. See, this is a non-terminal alkene, sorry, alkene. If suppose a terminal alkene is considered, like this. Now in this case, again cut it here. Uh, See, from this area at the beginning we get aldehyde. Because it is hot, it undergoes further oxidation to form carboxylic acid. Right? From the other end, this side, we get, of course, formaldehyde. But because this is hot, formic acid, it is hot. So even the next step also takes place. So this is further oxidized to carbon dioxide. So this is interesting. So whenever you got a terminal alkene, remember this area gives you carbon dioxide. Okay. So this is about oxidative cleavage. Let us consider the next one. See, it is addition of halogen and water. We can also say that this is the formation of halohydrin. Formation of halohydrin. Okay. Let me give you the reaction first, then we'll go for the mechanism. Taking the same unsymmetric alkene, let us consider bromine water. Bromine water is nothing but HOBr. This is hypobromous acid. Okay. See, as such, bromine reacts with water to form HBr and HOBr. So bromine water is generally considered to be the addition of HOBr. As usual, following Markovnikov addition, see the negative part of this reagent is OH minus. Let me add this to that double bonded carbon which has less number of hydrogens. Right. So this is 1-bromo-propan-2-ol. Okay. Now let's go for the mechanism. So in this case, just like what we have seen in halogenation, taking propene. See, at the beginning, just like what we have seen in halogenation, come on. This one attacks the bromine, and the other bromine goes out along with the bonded pair. Okay. See, this bromine gets attached across the double bond, forming a cyclic halonium ion intermediate. Same as what we have seen in the reaction with halogen. Cyclic halonium ion is what we get. Now this gets attacked by water. Now attack it here. As and when it attacks this carbon, from the side opposite to that of this cyclic halonium ion group, I mean from the opposite side of this area, because this is already closed. So this kind of an addition is called anti-addition. So stereochemistry here is anti. Regio is of course Markovnikov. Okay, we'll go for that. Now we get this. Methyl hydrogen. Let me straight away write this by removing the proton in one step. Just a second. Yes, this is anti. Okay. Now let me write that here in this case, regiochemistry is Markovnikov. Coming to stereochemistry, it's anti. Okay. So these are the two important things in this. Okay. Let me also give you one more example. Even here also it's, see, if suppose this is taken, this, with the HOBr. Now the products formed are going to be, look at this. See, as such, this double bonded carbon has less number of hydrogens. So the negative part goes and gets attacked there, and the positive one attacks here, right? Now, and that too, it has to be anti. Let me show you this way. If suppose it is this. Okay. Then here it will be bromine and then hydrogen, right? So this is how OH and Br are added anti to each other. Okay. Of course, the Markovnikov thing is also considered. Next, let us go for allylic halogenation. See, first of all, what is allyl? Let me say that this is vinyl. Ethynyl is vinyl, right? Now, if you consider this, just a second. Okay, that is vinyl. Next, if this is the case, it's called allyl. So it is proper to in aisle. Say here is the point of attachment, So start giving numbers from this carbon. This becomes proper 2 in aisle. Right? Okay. So that is allyl. These two are very important, remember. Now, what is allylic halogenation and what are the reagents employed for allylic halogenation? Let's see. The reagents used are, see, you can actually go for chlorine in the presence of sunlight, or instead of sunlight, you can also heat it to about 500 degrees centigrade. So chlorine in the presence of sunlight or chlorine heating. Okay, so that is reagent 1. You can also go for sulfuryl chloride with sunlight or UV light or heating. Then this is alkoxy chloride. In general, tertiary butyl group is what is generally used in this case. Even here also, in the presence of sunlight or UV light or heating. Then, of course, NCS or NBS. NCS is N-chlorosuccinimide. Okay. Then this NBS is N-bromosuccinimide. N-bromosuccinimide. Okay. Then what are these reagents? Let me show you. N-chloro, N-bromosuccinimide are the most frequent reagents used for allylic halogenation. Okay. Now, what is N-chlorosuccinimide? How is it prepared? Let's see. Same is the case with NBS. Now, we know that succinic acid is butane dioic acid. Now, when this butane dioic acid is treated with ammonia, let me take it this way for convenience. Ammonia. So this is succinic acid. With, of course, ammonia. Let us remove water molecule. Okay. Two water molecules are removed. Then we get this. CH2, C double bond O, C double bond O, then NH. Okay. Next. This is succinimide. Now on further treatment with a base. When treated with a base, H plus is abstracted and the bond goes towards nitrogen. Then we get a negative charge on this nitrogen. Now it is very much ready to attack chlorine. in this place, you can take bromine if you want NBS. Only difference is this. Now this one attacks on chlorine. Then this. C double bond O. Then this. N minus and Cl plus. Without bonded pair is plus. With bonded pair is minus. You all know this. That's it. So this is how N-chlorosuccinimide is prepared. Okay. Now let me give you an example. Yes. See, when this is treated with, say, NBS, now for convenience, let me take this CH3 as CH2H. Okay. Now, what is NBS? Come on. This is NBS. Now, go for homolytic fission in both the cases. A free radical here, a free radical here, a free radical here, a free radical here. So from this NBS, in fact, we get a bromine free radical overall. This is what we get from NBS. Okay, now, okay, let us keep it aside first. Let us keep this bromine free radical aside. And now, see, we got CH2 free radical, right? This is the free radical we got. Now, this is a 1 degree free radical, which is in fact less stable, isn't it? Now, this, of course, can be modified, can be rearranged. How? Come on, cut it. I mean, take homolytic fission. Okay. See, after taking homolytic fission, add these two. Then what do we get? We get a 3 degree free radical. Look at this. This is what we have. Now, this 3 degree free radical will go and get connected to the bromine free radical, or else let me show it here. Okay. Now, this will go and get connected, right? Then that will give a 3 degree product. I mean, a 3 degree free radical with bromine getting connected to that 3 degree free radical, which is a more stable one. Okay. Now, even from this side also, see, as it is from this 1 degree also we can get the product. Now look at what happens when the 1 degree is taken straight away. I mean, before modification. Even before modification also, we can write a product, but of course that will be a minor one. This one, right? As it is, if at all it is taken. This is from 1 degree. Now, we can actually go in some other way also. Consider this. Again, okay. See, there is another possibility. Even this also is allyl, right? If you consider this way, even this also is allyl, right? Okay, we'll consider that. See, just like from this area when this is allyl, from the other area, even this also can be taken as allyl, right? So there is another possibility. Again, go for homolytic fission here. I mean, even this also is okay. Combine these two. This will remain as such, to which we will be adding a bromine free radical. You can straight away add bromine free radical there. Of course, we got a major product here itself, planning some other things. Straight away, you get a bromine here or here. So two products can be written. If you write a double bond over here, then this will become your product. This is, of course, a 2 degree one. Okay. Even this way also is possible.